Hello, good afternoon. So in this screencast, we are going to talk about property changes upon mixing. Okay. So before we talk about property changes upon mixing, we're going to again let f, right, be an arbitrary thermodynamic state function. So that f, my molar f, is a function of temperature, pressure, and composition, where again xi would be however many mole fractions are needed to specify the state of my system. So for a binary system, I need just say x1. A ternary, I say need x2 and x1 because x3 is just 1 minus x2 minus x1. Okay, so f is an arbitrary thermodynamic state function, which is a function of temperature, pressure, and composition. Okay, and our partial molar f, okay, is by definition partial, and I'll write it as n times f, okay, or partial f total dni at constant t, p, and then j. Okay, so our partial molar property we can interpret as a response function. It tells us how our extensive f changes upon addition of some differential number of moles of species I, keeping everything else held constant. The other interpretation we can have of it is it's essentially the effective f due to component I in solution. So again, the easiest example I think probably to visualize is just thinking about volume. Okay, if I have a mixture of pure component 1, right, what is the molar volume? Okay, well the molar volume is the average volume per mole of component 1. Okay, or if I think of it, say, per molecule, right, where the volume, right, the average volume per molecule includes the excluded volume, the space actually occupied by the molecule, plus the buffer region around it. Right? Because if I picture all my molecules in, say, my liquid phase interacting in a box, right, they're going to occupy some space, but then there's going to be a distance between my molecules in that solution, right? The molecules aren't going to be on top of each other. Instead, there's some gap between them, okay? So when I calculate the average volume occupied per molecule, it includes an excluded volume plus some of that buffer region, okay? So now, that's, great. That's for component 1. So when I have a pure system, we would call that a homogeneous system, right? And that, the interactions, say, are uniform throughout, right? It's just pure component 1. Things change when I have mixtures. So now if I have a mixture of component 1 and component 2, and I were to calculate the molar volume of that mixture, okay, it's again the average volume occupied per mole, right, or per molecule. Okay, so what's meant by, say, partial molar f when I say its effective value? Okay, so if I think about the average volume occupied per mole or molecule of component 1 in that mixture, it's going to be different than the volume occupied per mole or molecule of component 1 in its pure component system. Okay, and what's going to be changing is not that physical space that the molecule occupies, but that buffer region, right? Because molecule 1's going to interact with molecule 2 different than 1 interacts with 1, right? So those molecules could be closer or further apart, so that buffer region could be further or smaller, depending on if they don't like each other or they like each other more than one likes itself. So our partial molar property is going to account for that, right? It's going to be our essentially the effective value in solution, right? It's going to account for the fact that these molecules interact in different ways with each other than themselves, and so the given property is going to be different than that in pure self. Okay, it's effective value in solution. Okay, and so hopefully trying to give you a picture of what all these things mean. But we'll play with it here, and hopefully you'll kind of, see that come out when we define property changes upon mixing. Okay. All right. So what do we mean by property changes upon mixing? Okay. So I'm going to imagine the case of a binary system. Okay. So I'm just going to think about a binary for now, so I can write down the equations. Okay. And I'm also going to think about a binary liquid for now, just because liquids are easy to picture. Thinking about, say, general chemistry lab. So when I think about property changes upon mixing, okay, imagine I have some beaker of component 1, which is at given temperature and pressure. Okay, so I have a beaker of pure component 1 at a given temperature and pressure, right? It's in a beaker, it's in my lab, so I know it's at atmospheric temperature and pressure. Okay, I also have a beaker of pure component 2, which is at the same temperature and pressure. Okay. So what I'm going to do is I'm going to mix those beakers together to form, or in a new beaker 3, okay, which will be component 1 plus component 2. Right? It's going to be composed of the mixture formed by mixing component 1 and 2. I'm going to do that so that it's at the same temperature and pressure. Okay, so pressure, not a problem, right? It's going to be the atmospheric pressure. Temperature here, we'll add or remove heat so that my final mixture is at the same temperature as those two initial beakers. Okay, maybe I have these beakers submerged in a massive bath that's able to absorb any heat generated or contribute any heat that needs to be removed from, say, the surroundings. Okay, but I'm going to mix it so that my final system's at the same temperature and pressure. Right, this is important. Right, so I'm mixing two beakers at the same temperature and pressure to form a mixture at the same temperature and pressure. Okay, same T and P though. Okay, that's important. So, I could have, say, an F1 of beaker 1, right, the molar F of component 1, right, in that beaker of pure component 1. Could have an F2, the pure molar F of component 2 in beaker 2, okay. And then in that final beaker, I'll have some F, right, I'll have some F of the mixture. Okay. So we're going to define delta F of mixing, okay, is being equal to F, okay, F being the molar F of my final mixture, minus the molar average F of those two beakers I'm mixing together. Okay, so for my binary system, this would be F minus X1 F1 plus X2 F2. Okay, so delta F of mixing is going to be F of my final mixture at T and P minus the molar average F of these two pure component beakers that I'm mixing together at the same T and P. Okay? Or if I want to think of this extensively, right, you could define a delta F mix total. My extensive delta F of mixing would be F total, okay, which is just N times F minus N1 F1 plus N2 F2, right? Essentially, all I'm doing is multiplying through by N, right? So maybe you'd prefer to see it as N times F, right? N times F or F total, it's the same, okay? So if I were to multiply by N, I'd have my extensive F of that final beaker minus, so it'd be moles of component 1 times the F of component 1. So this would be the extensive F, right? So you can think of it as F1 total. And 2 times F2 would be F2 total in the two beakers I'm mixing together. And then that would be the total F in that final beaker. Okay, so, what we're trying to get here with delta F of mixing is, again, this kind of idea, right? Mixtures are very unique and very interesting to study, right? In fact, right, I would joke I like to study mixtures as a hobby, right? That's what we do in my research group, right? We just think about mixtures and try and interpret what's going on in terms of the underlying intermolecular interactions or try and explain observed phase behavior. Okay, but if I think about this, right, the idea is in beaker 1, right, I have a homogeneous system. So in beaker 1, I just have, one molecule is interacting with one molecules. In beaker 2, I just have two molecules interacting with two molecules. Right? So I have two homogeneous mixtures. Okay? If I think about volume again, you can think in terms of volume, right? But I just have one interacting with one or two interacting with two. What happens now, though, is when I combine them, right, what complicates things is now I have cross interactions. So in addition to, say, one interacting with one and two interacting with two, I'll also have one interacting with two. Right? If I just think about things as being pairwise, right? Now I have one interacting with one, two interacting with two, and one interacting with one, two interacting with two, and one interacting with two. Right? These cross interactions are what make things complicated. So in this final system, right, these cross interactions are going to cause the effective, F's, say in my due to each component in that final mixture to be different than they were in the pure component state, right? So delta F of mixing, right, is going to give us the deviation, right? So it's going to essentially give us the effect of these cross interactions. It's going to show us, the difference in F relative to just that molar average of those pure component values, okay? And this might not make incredible sense now, but hopefully it will in due time. Okay, and actually let me keep the beakers up. So another way I could write this is if I just look at, say, this general expression. Okay, remember, so from our videos on partial molar properties leading up to Gibbs-Duhem equation, we showed that, how do I want to write this? We showed that F, okay, so let's say F in my final beaker, can be written as the molar average of the partial molar Fs of each component in solution. Okay, so if F now is at a given, okay, so remember F, okay, my final beaker would be at a given temperature and composition. Okay, F bar I, my partial molar F, right, is at a specific temperature, pressure, and composition. Right, it's composition dependent. Whereas, say, just Fi, okay, as I have here, right, that's just my pure component value, which is at a given temperature and pressure. Okay, so we showed in our partial molar notes that F is equal to the molar average of my partial molar Fs, or the effective values in solution at those conditions. Okay, so knowing that, what I can do is I can take this and I can substitute it in here in our expression for delta F of mixing. Okay, so if I just think of the general case, okay, that would give you then the delta F of mixing is equal to sum over I xi F bar I, right, that's just F, minus sum over I xi Fi, or collecting terms, just write a sum over I xi F bar I minus Fi. Okay, and I'm going to write delta F of mixing so I can box it in. Okay, conceptually, I really like this definition. Okay, why do I really like this definition? Well, okay, if delta F of mixing is kind of this departure term, right? So it's going to count for the fact that one molecule 1 interacts with molecule 2 different than one interacts with itself, right? And so now if I think of this, right, so partial molar properties we said are effective Fs due to component I in my mixture, right? Fi would just be the molar F of component I and pure component I, right? And remember, my partial molar F is equal to the molar F in the pure component limit. Okay, so this is my effective F in solution at a given composition. This is my molar F, right? So as if I had a pure component system. Okay, so delta F of mixing then is just the molar average of the difference between my effective value in solution at our temperature, pressure, and composition relative to that pure component value at T and P, right? So it's a molar average of these departure terms. Okay, now let's even think about things, right, of how these things could become useful. Okay, let's think about volume. Okay, volume is just always an easy one to picture. Okay, or enthalpy, right? Enthalpy is another easy one to picture. So if you think about enthalpy, say intermolecular interactions. Okay, if I have let's see, I mix molecule 1, solution of molecule 1 with the solution of molecule 2, and they form some final mixture. If molecule 1 likes molecule 2 more than molecule 1 likes itself, and maybe even that pair interaction of 1 and 2, that's more favorable than 2 interacting with 2. Well, if it's more favorable, what that means is it's going to have a lower internal energy or lower enthalpy, right? That cross 1-2 interaction is going to be at a lower energy, right? Think about my Leonard-Jones potential back in chapter 1. Okay, so what that would end up meaning then is, okay, then my effective enthalpy due to component I in my mixture is going to be lower, right? Because we're going to have these favorable cross interactions. I'm going to have these molecules interacting at closer distances because they really, really like each other, right? Lower energy, more favorable. And so what will end up happening is, your effective value is going to be less than your pure component molar value. So this term is going to be negative. Say it's negative for one or presumably both. That's going to lead to negative delta F of mixing. So now if I measure delta H of mixing to be negative, say, oh, right, delta H of mixing is negative. It must be that those molecules really like each other. Right? They like interacting with each other more than they do themselves. Right? Similar argument would be made for for molar volume. Those molecules really like each other. They're going to be interacting at closer distances than they would with themselves. Right? And so these property changes upon mixing, when I think of it in this context, become useful because I could gain some insight in terms of what's going on at a molecular level. Okay, cool. Okay. Now, having done that, so not blocking this with my face, let's look at, our standard thermodynamic properties, right? So remember, we're mixing at constant temperature and pressure, so there's no thing as delta P of mixing and delta T of mixing. But let's think of our other common thermodynamic properties that we'll look at. Okay, and so the first one would be delta V of mixing. Okay, so now delta V of mixing is going to be, so let's see, so delta V of mixing can be positive. Okay, it could be negative, okay, or it could be 0. Okay, so what would happen if delta V of mixing were 0? What that would tell us then is, right, the molar average difference between our effective value in solution and pure molar values is 0. So one case would be, the effective values are all the same as the molar values. Oh, that's pretty ideal. They're pretty comfortable with each other. Maybe they're all interacting in the same way, right? Or you could have some convenient cancellation of errors. Okay, but if I think more generally, a positive delta V at mixing. So what that would tell me is on average, the effective V in our mixture is larger than pure component V. And so on average then, it would tell me that our molecules are going to be further apart than they are in their pure component systems. On average, the molecules are further apart. Oh, so it sounds like a delta V of mixing that's positive. They might not like each other all that much, right? If they liked each other, then I'd expect them to be hugging on each other nice and close. So negative delta V of mixing, on average, the effective V of each component in the mixture is less than the pure component V. So on average, the molecules are going to be closer together in that mixture than they are in those pure states. So there must be some favorable interactions happening in my solution. Right? Cool. So just by thinking in terms of this, we're able to gain insight like that. Right? Cool. And this isn't a course in intermolecular interactions, but the more insight we can gain from data we measure is going to allow us to design the most efficient separation processes, right? The more we can understand what's happening in our system, the better we can understand how best to handle it, or best understand why we observe what we observe. Okay? So if you think about delta H of mixing, okay? Delta H of mixing could be positive, okay? And we'll look at each case individually. So delta H of mixing could be positive, okay? So when delta H of mixing is positive, okay, what does that mean? That means, on average, the effective enthalpy of each component in solution is greater than that of its pure molar self. So that would tell me that essentially, on average, in that mixture, the molecules aren't interacting as favorably as they did in those pure solutions, right? So it tells me I have some unfavorable interactions. Now, delta H of mixing also physically corresponds to something. Okay, so when I look at this mixing process, so I'm mixing at constant temperature and pressure. Okay, so if I were to do my first law energy balance, say for an open system here where the number of molecules is changing, my first law of balance would just reduce to Q is delta H. Okay, and so the delta H of interest here is delta H of mixing. So if delta H of mixing is positive, that means Q is positive. That means that heat needs to be added to my system to maintain that constant temperature. Okay, so delta H of mixing means heat needs to be added to my mixture. Okay, and we call this case endothermic. Okay, heat needs to be added to my system to maintain that constant temperature. And so heat needs to be added to maintain the temperature or to drive the mixing. And so that's going to correspond to unfavorable interactions. All right, next is going to be delta H of mixing less than 0. So if delta H of mixing is less than 0, we call this exothermic. Okay. So what does this mean? It means, well, on average, the enthalpy the effective enthalpy of each component in my mixture is less than its pure molar enthalpy. All right, so on average then, the interactions in solution are going to be more favorable relative to pure self, right? Interactions in that pure system. It's exothermic, so if delta H of mixing is negative, it means Q is going to be negative, so that means heat needs to be removed from my system in order to maintain that constant temperature. Heat needs to be removed from my system to maintain constant temperature, right? Hot, right? Yeah, I need to remove heat in order to maintain that constant T. Okay, exothermic, favorable interactions. Okay, last one would be a special case of delta H of mixing. Mixing is equal to 0. So that would tell me that on average, the effective enthalpy of each component in my mixture is the same as its pure molar self, or in the very special case that all of our interactions are exactly the same, right? And so, generally, that's kind of more the picture that comes to mind, is that when all your interactions in the mixture are the same as in those pure component states, right, it would lead to an athermal solution, right? Or delta H of mixing is 0, and it gets a special name of an athermal solution, okay? And athermal solutions become really important in the polymer world. And essentially, it's more so that enthalpy or the interactions are just negligible compared to entropy due to mixing these big, big molecules with really small solvents. Okay, but that's another topic. All right, so athermal would be delta H of mixing is equal to 0. Okay, one thing we'll prove for the case of an ideal gas, okay, but you'll just have to leave it to faith for now. We won't provide a rigorous proof except for the ideal gas case, is that delta S of mixing is always going to be positive. Delta S of mixing will always be positive. Okay. Now, if you think about your mass transfer course, your separations course, this is what makes separation processes so expensive, right? Because if I'm taking, if I think about a separation process, essentially I'm trying to go in reverse, right? I have a mixture of, say, two components. If it's distillation, I'm trying to create, say, a vapor stream which has a higher concentration or higher mole fraction of the most volatile component than that mixture I started with. And my bottoms, or I'm going to have a liquid stream, which is going to have a concentration of the least volatile component that's larger than that mixture I started with, right? And, effectively, you're not going to get to these pure states, although that would be pretty amazing, right? But the idea is you're trying to go in reverse, okay? So if when I mix those two beakers, delta S of mixing is increasing, okay, it must be then to go the opposite way as I would want to in a separation process. Delta S of mixing, or the entropy of my system, needs to decrease, okay? And so it's the fact that you're trying to decrease the entropy of your system which causes those animals to be so expensive. Okay, so we'll prove for an ideal gas that delta S of mixing is always positive. One way you can kind of think of it, interpret it, is if I think instead of molecule 1 is being say red molecules, molecule 2 being green molecules, I mix them to form this mixture. Okay, the idea is the number of configurational states available to my system has increased, right? So it's not, if I have a beaker of pure component 1, pure red balls, and let's say those are indistinguishable molecules, I swap the position of 2 red balls, I haven't created a new configuration. Okay, but in that mixture, I swap the position of the molecule 1 and 2, right? That's a new unique configuration, right? So the number of states available to my system has increased. Okay, cool. Then the very last one, okay, that we could show if you wanted to from our combined statement, the first and second law, but we won't, okay, is that delta G of mixing is going to be less than or equal to 0. Okay, delta G of mixing is going to be less than or equal to 0. Okay, so if you ever calculated delta G of mixing to be positive, what's going on? Okay, and we need to put this in context. So delta G of mixing is less than or equal to 0. Okay, what I'm assuming here is when I take a beaker of pure component 1 and a beaker of pure component 2 and I mix them, I'm mixing and forming a homogeneous mixture. So I'm taking a beaker of pure water, a beaker of pure ethanol, and I get a mixture of water and ethanol. Okay, What would happen though if I took a beaker of pure water and I mixed it with a beaker of pure octanol, right? Essentially an oil. Okay, what would happen there is that in my final mixture, I'd get phase splitting, right? I would get an octanol-rich phase in equilibrium with a water-rich phase. Okay, so what would happen, right, is for that process, right, I don't have a homogeneous solution that forms because it would result in a delta G of mixing that's positive, right? That's unfavorable, right? That means that my Gibbs free energy of my mixture is increasing, which thermo tells us is not what I would expect to happen at equilibrium in a given TP, and so I would get phase splitting so that my system can reduce its molar Gibbs free energy. Right? The idea is I get phase splitting because by splitting phases, the Gibbs free energy of that resulting two-phase system would be lower than that unfavorable homogeneous mixture. Okay, so when I say delta G of mixing is always less than or equal to 0, right? Again, we're thinking about mixing beaker 1 and beaker 2 to form a homogeneous mixture, right? A completely miscible system. Okay, so if we're going to form a completely miscible system, it must be that delta G of mixing is less than or equal to 0. If delta G of mixing is greater than 0, well then guess what? You're not forming a homogeneous mixture. Okay, all right. Well, that's all for these notes. Next, we'll work out expressions for delta V, delta H, delta S, and delta G of mixing for the case of an ideal gas.